here's where we are. Is we're going to be talking about molarity and ways to calculate molarity. We're also going to talk about molality and the difference between molarity and molality. I'm also going to show you how to calculate percent by mass, because those are three ways that chemists use to express concentration of a solution. I want you to be able to calculate all those. Then we're going to talk about your actual mixing of a solution. What do you actually have to do once you know the numbers and the calculations? Then we're going to practice some dilution problems. And finally, we're going to finish with some stoichiometry and some acid-base reactions. So there's our format of where we're going with the calculations in this. So now we're going to start with calculations. Okay. So as we begin, our big picture idea of what we're doing calculations for is concentration. Concentration in chemistry is a lot of different units. We use a lot of different units to express concentration. Every one of the units that we use is simply a ratio of the solute divided by the solvent. It's simply a ratio of the stuff that is being dissolved versus the stuff that is doing the dissolving. So the solute is the stuff that we're putting into whatever it is that we are making the solution with. The solvent is generally a liquid substance. Sometimes the solute is a solid, sometimes the solute can be a liquid. Generally, the solvent is going to be some sort of liquid solution. All right, so we have percent by mass as one way to express the concentration between solute and solvent. We have this idea of molarity, which we're going to use extensively in this class, as well as Chem 152, and then molality, which is used in this class a little bit and a whole heck of a lot more in Chem 152. All right, percent by mass. We're going to use the same calculation with the same salt water solution. So I want to make a salt water solution. So I'm going to take plain old table salt, good old sodium chloride, and I'm going to put it into my solvent, in this case, which is water. So the solute, the thing that is being dissolved, is the sodium chloride. The solvent, in this case, is the water, the thing that is doing the dissolving. Let's pick some random number. I'll say 8.5 grams of my sodium chloride that I'm going to put into the water. And of my water, we'll say I have 150 milliliters of water to work with. All right. Let's start first with percent by mass. Percent is something that chemists like to use a lot of. What is the basic formula for percent? Part over total, right, times 100, since it's a percent. So that's the basic idea of all percentages. And chemists love to use percentages because it's much more descriptive. So if we're going to calculate our percent by mass, and there is percent by volume, but we're not going to go into that today. If we want to calculate percent by mass of this particular solution, what is the part? The 8.5 grams. So I got 8.5 grams of sodium chloride is my solute. That's the thing that's being dissolved. Here's the tricky part. What am I going to use as my total? There's a couple of different ideas here that we have to synthesize in order to figure out the total. First of all, that's not a mass, right? That's a volume. What do I know about water that's specific only to water that I can use to convert volume into mass? Molar mass is helpful for grams per moles, but I want to convert volume to mass. The density of water is what? Is 1. 1 what? 1 gram is 1 milliliter, right? That means a gram of water takes up a volume of 1 milliliter. The volume of 1 milliliter of water weighs exactly 1 gram. Now, that's not always true of all liquids. For example, most alcohol has a density of about 0.9 or 0.8 grams per mil. So it's much less than 1 gram per mil. Something like corn syrup has a density of about 1.2 grams per mil, right? So those density values you can use to make conversions. In this case, water's density is pretty handy. It's 1 gram per mil. So if I've got 150 mils of water, how many grams is that equal to? 150 grams. All right. So that's the first piece of information I need to have in order to decide on what my total is. Is that my total? No, it's not. I need the total of the entire solution, including the solute. So what's the total of the entire solution, including the solute? 158.5 grams of solution. Right? Because that's the total. And the total has to be the solute and the solvent together. So we take 8.5 divided by 158.5, multiply that by 100, what number do we get? 1.36? 5.36? So we have about a 5% solution of sodium chloride. Okay? All right, that's one way to express concentration. We also need to talk about molarity. Okay? Molarity, we use capital M to express molarity as an abbreviation. Molarity is equal to moles of solute divided by liters of solution. So that's molarity. There's our formula, our algorithm for molarity. Molality is slightly different. Molality, we use lowercase m, and molality is, let's put molality up here. Molality is equal to moles of solute divided by kilograms of solvent. That's very different than molarity. So molarity units are moles per liter, moles of solute divided by liters of solution. Molality is still moles of solute on the top. And that's because chemists, we like to describe solution concentration in terms of number of pieces. But now, rather than the volume of the entire solution, we're only concerned with the kilograms of the solvent. We generally tend to use molality when temperature may influence. Why is that? Let's think about that. Capital M, molarity is moles per liter. Molality is moles per kilogram solvent. This is liters of solution. All right. What would make a difference not used when temperature changes? This is one that's used if temperature changes or is in some sort of influence. Why would temperature, what would change about molarity if temperature changed? Go ahead.
Temperature increases how much it reacts. So when that change, how does it react?
Okay. Instead of just we could dissolve more salt in the solution if we had water. But in terms of the value of molarity, how would that change, the value of molarity change if, say for example, the temperature of your solution went up? What would change? Would moles of solute or liter of solution change? Yes. Liters of solution. What happens to the molecules of a substance when you start heating it up? The molecules start moving faster, right? As they move faster, does it not stand to reason they would need more room to move around? So the volume of water actually expands a little bit when it's heated up. You can see this in an experiment that I used to do in class, where you can take a beaker of water, put it on a hot plate, turn on the hot plate to high, and in that beaker of water, we're going to place a test tube. The test tube would be completely full of water, and then it would have a stopper on the top of it. And in that stopper, there would be a glass tube that would allow some of the water from the test tube to go up into it, and we would fill it up almost to the top so that the top of the tube would have a tiny little bit of airspace left in it. Then we would turn this up, the water would start to heat up. You could actually physically see the volume of water increase as the temperature went up, and that's because the molecules of the water are moving a little bit faster. As they move faster, they take up more room and the water expands. This is going to be the reason that our shorelines change in the United States on the West Coast and the East Coast if global climate change isn't brought into check. Global climate change includes the idea that some areas are going to be warmer, some areas are going to be colder, But overall, the planet itself could rise in overall average temperature, even just a single degree. If a single degree temperature increases on the entire planet, people say, oh, the North Pole, the South Pole, the polar ice caps are going to melt. And they'll run off the land and they'll be added, that volume of water will be added to the ocean. And that's what's going to raise the ocean level. Okay, it will raise it a tiny bit. However, what's going to be much more responsible for the overall increase in the volume of water in the oceans is going to be the thermal expansion of water. The fact that it actually gets bigger as you heat it up. When we take all that water that covers all the surface of it, and there's actually more surface area on the Earth covered by oceans than there is land masses. And think about how deep those oceans are, the volume of water there. If we raise the temperature of all the oceans a single degree, they all expand a tiny bit. What's that going to do to the coastline in California? It's going to inundate places like Malibu or San Diego, or places that are right on the coastline on the East Coast. Places like Long Island, which are between 12 and 18 inches above sea level, they're all going to go underwater. A lot of islands off the coast of New Jersey, a lot of beachfront property is going to be ruined as a result of global climate change and the thermal expansion of water. So with that idea in mind, that's why we tend to use molality as our reference when temperatures change. So let's do the same calculation with our same solution with both molarity and molality. All right. Since molarity and molality have as their numerator moles of solute, what should I do with my original situation here, my 8.5 grams of water? What do I need to do? Convert to moles, right? The universal method, if you have absolutely no idea how to solve a chemistry problem, and you come up to something, you go, yep, that's a chemistry problem. You have no idea how to solve it. Find something, you convert to moles, right? All right, so we're going to go grams of sodium chloride to moles of sodium chloride. When you go from moles to anything else, 1 is always the coefficient in front of moles. If I look at the mass, the molar mass of sodium chloride, I look at sodium is about 23 grams per mole. Chlorine is about 35.5 grams per mole. So it's about 58.5 grams per mole. All right, somebody with a calculator. What's 8.5 divided by 58.5? All right. Sig figs, I might round that to 0.15, and I'm going to use capital M, molarity, of NaCl. Remember, molarity means moles per liter. So that's the unit and what it means. You've got to label it just like that. Oh, wait a minute. I'm not right. I didn't finish this problem, did I? That's not molarity. What is that? That's moles of NaCl. All right, just checking to see if you guys are awake. So I take my 0.1. Actually, we won't want to round that to the very end. So we'll use our 0.145 moles of NaCl. And now what do I need to do to that? Divide by remember the formula for molarity is moles of solute divided by liters of solution. So how many liters of solution did I have in my original salt solution? Okay, I had 150 milliliters, right? So I got to change milliliters to liters. So in essence, I'm dividing by 1,000. So it's 0.150 liters of solution. And we're going to assume that the NaCl doesn't take up much room. All right, what's 0.145 divided by 0.150? What is that? 966. All right, there's our answer. Molarity of sodium chloride. All right, let's do molality too. Molality, baby M. What's going to be my numerator position? Same moles of solute, that hasn't changed, right? I still have 0.145 moles of NaCl. Now I have to divide it by the kilograms of solvent. Right, how many grams of solvent do I have? I have 150 grams of solvent, so I got to go from grams kilograms, right? What's bigger, a kilogram or a gram? Kilogram's bigger. There's 1,000 of them in there. 1, 2, 3. Now, it is going to come out to be the same in this particular instance because the solute is water, whose density is 1. If the solute was alcohol, where the density is less than 1, or something like corn syrup, where the density is greater than 1, this number would be different. But for this particular set of problems, the number is the same. All right, so now we know how to make concentrations. And now we're going to do actually something that I had to do when I was a baby teacher. You're going to make a solution. And it's something I actually had to do when I was a baby teacher. I graduated with my chemistry degree from NAU, and I walked into my first chemistry classroom, and it wasn't like this here, where we have a wonderful lab tech that mixes everything up for me, sets out all that equipment for you, and then when we're done, comes in, cleans everything up, and does all the hazardous waste disposal. And I had to do that as a chemistry teacher. So I walked into my first stock room as a baby teacher, and I think about 1983, and I looked on the wall. There is my first bottle of NaOH, and I go, okay, NaOH is a solid, and I want to do an acid-base lab with my students. And so I said, all right, I need to create 750 milliliters of 1.5 molar NaOH. That's how much my students need to do their experiment. So I got to make a solution. So there's my dry stuff on the shelf, right? I need 750 mils of 1.5 molar NaOH. Well, based on our definition of molarity, which is moles of solute divided by liters of solution, what can I do here? I go up to the stock room, I got to get my sodium hydroxide, the dry stuff, off the shelf, and I'm going to make a solution out of it. Any ideas on the math? Yes?
You're basically just going to multiply 1.5 times 0.75 liters.
Well, it looks like what you might be saying or what you're doing in your head is we've got the volume here, right? So we know that, correct? We know the volume of the solution that we need, in this case 750 mils. I know the concentration, right? So I got those two pieces of information. I know the volume, I know the concentration. So my unknown is going to be my moles of solute. So if I want to use a little algebra and solve for moles of solute, algebraically, what's that going to look like? Well, not the numbers, just the symbols. I'm going to take molarity and I'm going to multiply it by the volume in liters. That's another version of this formula that you are going to use quite extensively in this course. Remember when I said you have to solve chemistry problems, most of the time you've got to convert something to moles. If you've got a volume and you've got a concentration, from those two pieces of information you can get to moles. Now you can't count out moles, but once you get to moles, what can you convert to that you can measure? Grams. So this is one iteration of this formula that you're going to use significantly in this course, so just right now commit it to memory. All right, so if we're going to figure out moles, in this case the solute of NaOH that I need in order to make my solution, I'm going to take my concentration, in this case 1.5 molar, and remember that means moles per liter, that symbol. I'm going to multiply it by my volume, in this case 750 milliliters, but am I going to leave it as 750 milliliters? No, what do I need to do? I've got divided by 1,000, and why am I doing that? I want to go to liters, right? So I want to eliminate milliliters, and I want to know how many liters I have. So I'm going to change that 0.750 liters. Now, somebody with a calculator, what's 1.5 times 0.750? 1.125. And what are my units here? Since I'm multiplying moles per liter times liters, what are my units? Moles of what? Of NaOH. All right, can I go into the stockroom shelf and take my bottle off and count out 1.125 moles of sodium hydroxide? No, not in this lifetime you can't. So what would I do instead? I got to convert moles to grams, so I'm going to take 1.125 moles of NaOH, and I'm going to go from moles of NaOH to grams of NaOH. I know the molar mass of this because I've mixed up tons of sodium hydroxide. It's 40 grams per mole. You guys can work that one out on your own. That's just something I have in my memory banks. So what's 1.125 times 40? 45? 45 grams, 45.0 maybe, grams of NaOH. All right, is that my answer? Well, sort of. I get to this point, physically, what am I going to do to make my solution? Now, here's where, and this could very well be one of the subject questions on your next exam scheduled for a week from today. Anyways, it's scheduled coming up soon. That you have to describe how you would make a solution. If all you do is this and tell me 45.0 grams, that doesn't tell me anything. What am I going to do with that 45 grams? With 750 liters? Well, wait a minute. I think 45 grams of sodium hydroxide probably would take some volume itself, wouldn't it? I think that 45 grams of sodium hydroxide. Okay, say for example I had a 750 milliliter volumetric flask. Here's my volumetric flask. And right up to that line is exactly 750 milliliters. And this is what chemists use to do these sorts of activities, is they use a volumetric flask that gives you a very specific volume. So what am I going to do with this volumetric flask? What am I going to put in it? My 45 grams of NaOH, right? All right, so there's my little pile of NaOH, solid. I put it into my flask. Now what should I do? Remember the definition of molarity. Here's the definition. Moles of solute divided by liters of solution. So that means whatever volume the solute takes up has to be included in the total volume of the solution. So if I start with my that says 750 milliliters there. That's right. I'm not on that. There's my NaOH, which is 45.0 grams. I'm going to add enough water to equal what total volume? 750 mils. That doesn't mean you're going to add 750 mils of water. It's probably some amount less than 750, right? Because this 45 grams of sodium hydroxide is a pretty good pile of stuff. And that's going to take up some mass too. Or some volume, excuse me. So you add enough water. So if you were writing the essay portion on your next exam, it said, how would you make this solution? The very first thing you would have to do is, of course, show the calculations. And then you would say, I would take a flask with a volume of 750 milliliters. I would put my 45 grams of sodium hydroxide into the flask, and I would add enough water to equal a total volume of how much? 750 milliliters. All right? So that's how you make the solution if you're starting with the dry stuff. Well, sometimes you're not starting with the dry stuff. Sometimes you walk into the stockroom shelf, and there's your NaOH, but now it's an aqueous solution. And say it's pretty concentrated, it's an aqueous solution that we can make other stuff from. And we're going to say it's a 6 molar aqueous solution. Okay. So it turns out I need 750 milliliters of 1.5 molar. We use the same thing. Well, I've got the concentrated stuff here on the liquid, and I've got some more dilute stuff. So it turns out you can use this relationship between molarity and volume and set up an algorithm that expresses that between the concentrated version and the dilute version. And here's the premise that we're operating under. I'm going to take some concentrated amount of the substance and I'm going to add water to it, right? I'm going to dilute the substance. If I take some amount, say I took 10 moles of substance, and I put them into a volume of water that was much larger than the original one it was in, will the 10 moles change anything? Well, they would just simply spread out further from each other, right? So I would still have the same number of moles there. So what this expression is using as the mathematical part of this is the fact that molarity times volume equals moles, right? And so moles of the concentrate that I take out of my container and I add water to hasn't changed any. I still have the same number of moles. So what I'm doing is simply expressing the ratio of the concentrated moles to the dilute moles. So this is the algorithm you can use. And you say, all right, I walk into my stockroom shelf, and on the shelf is my concentrated version. So there's my concentrated side. So my concentrated molarity is 6 molar. So I'm going to say 6 molar on this side, right? So I'm filling in the numbers for this algorithm. What's the volume of concentrate that I'm going to need? We don't know that. We don't know that. So what are we going to call it? X, right? Did I tell you guys my algebra joke? Hey, algebra. We don't know where your X is. Right? Because they're always asking to find X in algebra. And we don't know why she left either. Tell that one to your algebra teacher. See, intellectuals understand intellectual jokes. You guys are all intellectuals. The molarity of my dilute solution is what? 1.5, right? That's the stuff I want. Concentrated, the number's bigger. Dilute, the number is smaller. What volume of the concentrated stuff do I need to take in order to make my dilute? What's the volume of my dilute stuff that I need? 750 milliliters, but am I going to leave it in milliliters? No, because remember molarity is moles per liter, and if I multiply moles per liter by liters, molarity, or moles is what cancels out, so I'm going to put 0.75 liters. All right, now we can do a little algebra magic. Solve for x. Start with the calculator. What's x? 0.1875. All right, what are my units there? Liters. So now, you got to tell me a story. How are you going to make the solution based on concentrate? You have to do calculations first. So you say, all right, I'm going to take how much of the concentrated solution? Or 187.5 milliliters, right? You guys all measure out 187.5 milliliters, right? So I take the 187.5 milliliters, what am I going to do with it? I'm going to put it in a flask, right? So I'll take my 187.5 liters, I'm going to put it in a flask. So there's my 187.5 milliliters. What am I going to add to 187.5 milliliters? As much water to equal a total volume of 750 milliliters, right? So you could tell me a story about how you would make a dilution, right? Here's the basic formula. All you have to do is interpret. The math isn't hard, right? The math isn't hard. It's interpreting the story and plugging the numbers in based on the story. That's the hard part. Add, subtract, multiply, and divide. You guys can all do that. All right, so that's the dilution. Now we get to our favorite, stoichiometry, involving concentrations. Okay, take one of my favorite metathesis reactions, double replacement. This is the one that we talked about before. That's the bright yellow precipitate. Both of these things start out as clear, colorless solutions, aqueous solutions, and when you put them together, they make this bright yellow precipitate. You go, holy smokes, there's definitely a chemical reaction there. What we get as a product is potassium nitrate as one of the products, and the other product we get is lead iodide. Now, are those the correct nomenclature for those two compounds? How about this one? Is that correct nomenclature for potassium nitrate? It is. Is that correct nomenclature for lead iodide? Not so much. I got to fix that. What do I got to do with this one? PbI2, and that's because the ions retain their charges that they have as reactants when you make products. Now, knowing what you know about solubility rules, which one of these is probably the aqueous solution? The nitrate, and that's because nitrates are infinitely soluble. They never precipitate with anything. Iodides are often insoluble, especially when they come into contact with lead. All right, so we got to balance this. 2 there, and 2 there balances it, right? All right, so say, for example, in this experiment, I come in and I go, all right, I've got, let's see, I got 50 mils this stuff, and the concentration of the stuff is 0.30 molar. And I've got 0.40 molar of this stuff, and I want to know how many milliliters it's going to take me of this stuff to completely react every single smidgen of this stuff that I have. Right? This is looking like a BCA to me. I like BCA. I'm going to be using BCA almost every single week in lab starting next week. So if you don't know how to do BCA right now, I suggest you put your thinking caps on and figure it out. Okay. BCA, what are the units that you have to use to fill out a BCA? Moles. Can't use grams, can't use volumes, can't use concentration, none of that. You've got to convert to moles. So, based on the information I have about each of my reactants, which one of those things can I get moles out of? Lead nitrate, right? Because I've got the volume, I've got the concentration. So moles is equal to the concentration times the volume. So I'm just going to plug that in. The concentration in this case is 0.30 molarity times the volume in liters is how much? What's the volume in liters if it's 50 mils? 0.050 liters. All right. So what's my answer here? 0.015. And what are my units here? Moles of what? Lead nitrates. All right. Now I've got some information I can work with. I've got a molar amount. I'm going to put that into my BCA as my before. So 0.015 moles of this stuff is what we're starting with, right? Now if we look at our balanced equation, which one do I use more of? Do I use more lead nitrate or do I use more potassium iodide? I use a lot more of this by a ratio of twice as much, right? I have to have twice as many moles of that as moles of that in order for the reaction to occur. So if I got 0.015 of this, how much of this stuff would I have had to have in order to react all that 0.015? 0.030 moles of that, right? So I'm going to use up all that. I'm going to use up all that. I have none of that left over. But that doesn't tell me the answer to my problem, does it? The problem asked me, how many milliliters of this stuff do I need? Does this give me the answer to the problem of milliliters? No. What do I have that can get me closer to milliliters? I got moles of this stuff. What else do I have? And I got molarity. All right, so if we know that molarity is moles per liter, it looks like what I want to solve here for is volume, right? So if I want to solve this algebraically for volume, how would I manipulate this algorithm to solve for volume? It would be moles over molarity. All right, let's just plug those numbers in. What's my moles that's going to go on the top? There it is right there. See? BCA is super useful as long as you know what the heck it is that you're doing. 0.03 moles. What is my concentration? 0.40. See how I drew the picture? Physics taught me to do this. You write the equation, you write the variables that pertain to that particular reagent in the equation, and it's sort of like drawing a picture in physics, right? I always have you draw pictures of the force this way and the force this way and the frictional force and which way they're going and all that stuff. That's always very helpful. All right, so what's 0.03 divided by 0.4? 0.075? 0.75. What are my units here? Liters, right? Because remember, this is moles per liter. When you see capital M, you know moles per liter. So moles cancels. My final unit is in liters, and it's liters of potassium iodide. I could change that to milliliters if the question asked for milliliters. What would be the milliliter value? 75 milliliters. All right, so it would take about 75 milliliters of this 0.40 solution of potassium iodide to react every smidgen of this. Well, what if the problem asked for something else? What if the problem asked, what mass of lead iodide are you going to make? That could be another kind of problem. Well, that can also be answered by a BCA. In a BCA, remember, initially, before you put the reactants together, the before situation of your products is going to be that there's none of them there. Now we look and we say, we got a 2-to-2 ratio, we got a 2-to-1 ratio, or we got a 1-to-1 ratio. If I want to know if I burn up 0.030 moles of potassium iodide, and it's a 2-to-2 ratio between potassium iodide and potassium nitrate, how much of potassium nitrate will I make? Same amount, plus 0.030 moles. So in the end, I'm going to have 0.030 moles created. Same thing here. I can compare 2-to-1, but I think 1-to-1 is easier. And what you want to look at is the change row in order to determine how much of the other thing is reacting. So it's a 1-to-1 relationship here, right? If I burn up 0.015 of that, how much of that am I going to make? Same amount. Plus, and make sure you keep the pluses and the minus. I promise that's going to help you a ton when you get to Chem 152, whether I'm your teacher or not. All right, so the question asks, what mass of lead iodide would I have? How could I figure that out? Moles to grams. So I take my 0.015 moles of lead iodide, and I want to go from moles of lead iodide to grams of lead iodide. Just figure out the molar mass, do the math, and that will tell me how many grams of lead iodide I would have made in this particular situation. We should, I agree. How about an acid-base one? Because you're going to be doing titrations next week. So that would be very timely in order to learn the acid-base one. And I noticed from the quiz that there's some people that I think are a little bit weak on acid-base reactions. All right, let's do some acid-base ones. We'll take good old sulfuric acid, an aqueous solution, and we're going to add it to our favorite base, good old sodium hydroxide, probably the most common base in the laboratory. All right, add those two things together. My products I'm going to get are sodium and sulfate, which in this case is the salt, right? Acid-base or neutralization reactions, you always get a salt and what other thing? Water. What's the formula for water? Good old H2O. And we're going to put liquid because it's a pure substance when the H's and the OH's come together. Let's check our nomenclature. You always got to write new nomenclature for products. Well, we know that's the right nomenclature for water because we all know that, right? What about sodium sulfate? Is that the correct nomenclature for sodium sulfate? Not so much. What do I need to do? I got to have a 2 there. All right? Is that going to be aqueous solution or is that going to be solid, liquid, or gas? Aqueous solution. All right. Now we got to balance it. Make a 2 there and a 2 there balances things. All right. So in this reaction, I'm doing what's called standardizing my sodium hydroxide. I've got some acid, and I'm going to have 50 mils of my acid, and my acid was 3 molar. And I don't know the concentration of my base. That's what I got to figure out. But I do know that it took me 75 mils of the sodium hydroxide, whatever the concentration of it was, to neutralize everything, because when I add the acid and the base together, I had an indicator. And the indicator told me when everything was neutral, right? Turned pink or whatever it is, whatever indicator it was that you used. Okay, well, I'm liking BCA. And the phosphoric acid lab that you do next week, you're going to have to do this activity before you actually get to do the lab. I will actually ask you to do this. All right, BCA. Well, got to fill it out in moles. What can I get moles out of? Can I get moles of sulfuric or can I get moles of sodium hydroxide based on my starting information? Moles of sulfuric. So I want to take the volume and the concentration. So moles of sulfuric is equal to the concentration, in this case 3 molar, times the volume, which in liters is 0.050 liters. All right, somebody with a calculator, what's 3 times 0.05? Are we like 0.15? I'm not good at multiplying decimals. What is it? 0.15. 0.15. What are my units here? Moles of H2SO4. All right, so now I can put that in my BCA, and I'm starting out with 0.15 moles of this. I got to use all of it up in the neutralization reaction, so I have none of it left. Well, I know the relationship between sulfuric and sodium hydroxide is a 1-to-2 relationship, right? So which one do I need more of? Sodium hydroxide. I need twice as much of that. So what's twice as much of 0.15? 0.30. See, these are kind of fun. You get used to it. Only a chemist would say that, right? But this is fun. Let's finish the last part, the back end of our BCA, just for fun, since we are having so much fun. What would I compare my sodium sulfate to? What would be the easiest one to compare to? Probably sulfuric, right? Because it's a 1-to-1 relationship there. So if I burn up 0.15 of these, how many of these am I going to make? 0.15. So I'll have in my container, at the end of my experiment, 0.15 of those. My water, what should I compare it to? The sodium hydroxide or the sulfuric? Sodium hydroxide. So I burn up 0.3 of those. I'm going to make how many of these? 0.30. And then I'm going to have those. All right. So the question asked, what's my concentration? Have I answered the question? No. What do I have that I can use to answer the question? I got my moles. What else do I have? I got the volume, right? And molarity is equal to moles per liter. Isn't that the two pieces of information I need? Right? So I just plug in the moles. In this case, 0.30 moles divided by, what's the volume of the sodium hydroxide? 0.075 liters. All right. So here with the calculator, it's 0.3 divided by 0.075. 4, the number 4. That's easy. 4 molar NaOH is what we have. And that's actually something that you are going to do this semester. I'm going to give you an acid that you know the concentration for. You're going to titrate it so you'll know the volume that you added to the base. You'll know the volume that you added to the base, and your job will be to determine what the concentration of the base is. And it's exactly. Any questions? All right, we are done with chapter 4. That's it. Make sure you get in there and attack that homework. It is a lot. This is a lot of stuff to know. It all kind of relates to Chem 130, doesn't it? Wouldn't you think so, Jared? Yeah, it is. It is. But do you see the connection that BCA has to flowchart of stoichiometry? Is it starting to become a little more apparent to you? Okay, if that's the case, then you are integrating that intellectually, and your learning is going to be deeper. And I promise, whether you take me or somebody else for Chem 152, you're going to be sending me vibes. You're going to go, oh, thank you, Dr. Wood. Thank you for making me do this.